Hi, and welcome to Weekly Physics and CSZC with Sir Danny. Today we're going to talk about electric flux as the last part of our session on electrostatics 1. So we're going to understand or talk about what definition of electric flux and how it is related to electric field. And of course, if it's related to electric field, then it is all should be also related to the electric or electrostatic force. So let's begin with the definition of electric flux. An electric flux is defined as the electric field passing through an area of the surface, and the surface should be projected in a plane. Now, if there is an electric field passing through an area or through a surface area, the output of the field passing through the area is what we call the flux. Okay, so if there is an input of electric field, then there would be an output of electric flux. So electric flux only happens when an electric field passes through a surface. So the surface should be a two-dimensional surface. A two-dimensional surface. Or a since it's a surface area, it's either one or two dimensional. But majority of the problems in physics uses on basic electric flux uses only one dimensional object, one and two dimensional object. Now there are instances that it's a three dimensional object, but we only use uh, later on we will use uh, how do we use electric flux equation in a certain problem. And of course, electric flux is defined mathematically as phi, as a Greek letter phi, which is equal to the product of the electric field passing through the surface area. Now, the surface area should be perpendicular to the electric field. Uh, it shouldn't be parallel. It shouldn't be uh, it should be perpendicular. So if the electric field is passing, then there would be an electric flux if it passes to the perpendicular surface area of a certain object. Of course, if it's inclined on a certain plane, or it's projected on a certain plane, we use the laws of cosines. We were able, using the law of cosines or some geometrical laws, we can derive another equation as of electric flux as phi is equal to EA cosine theta. And primarily, if we have an irregular surface, we can use also the second equation, charge with respect to the permittivity of free space, or Q is equal to epsilon naught. Now, how did we able to come up with this particular equation? So let me show you how we were able to come up with this equation. So our goal is we know that phi is equal to EA, which is also equal to Q all over epsilon naught. Now, epsilon naught is a physical constant. It's a permittivity of free space, which has a value of 8.56, which has a value of 8.85 rather, 8.85 times 10 to the negative 12 coulomb square per Newton meter square. Now, later on, at this point in time, let us try to derive this second equation. Now, let's begin deriving the equation using this one, this equation. We have EA, we have phi is equal to EA. And we all know that EA is equal to what? Okay. EA 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 is, or E rather, E is equal to F all over Q or K Q R squared. Now let's use this equation. Let's fuse this equation to E. Okay? Let's substitute this equation to E. So we can write here, we can write K Q R squared times A. But the question is, what is the area? Now, if we use the best regular shape that we can use, since it is a charge, we can use a sphere. Let's use sphere. What is the sphere? What is the area of a sphere? The area of a sphere is equal to 4 pi r squared. Okay? We have 4 pi r squared. Now, please take note of this equation. We have phi is equal to kq r squared times 4 pi r squared. Now let's write that in the other sheet. We have phi kq r squared times 4 pi r squared. Now we can simplify this one right away. Now let's simplify this one. This equation. If we multiply these two terms with the r square, so we multiply this one, we will just have k times q all over r square times 4. No, rather, we will just have kq 4 pi. We will just have kq 4 pi. What happened to r square? R square is, we divide both sides. We have simplified r square, that's equal to 1. R square divided by r square, that's equal to 1. So we have kq 4 pi. Now, how does this kq 4 pi is equal to q all over epsilon naught? How? Okay. The answer lies within the Coulomb's constant. How did we get k? K is, how did we get k is that k is equal to 1 all over 4 pi epsilon naught. Okay. So the Coulomb's constant, if you try to input in your calculators 1 all over 4 pi epsilon naught, that will give you a value of approximately 8.9 times 10 to the 9, or just 9 times 10 to the 9 Newton meter square per Coulomb square. Now, using this formula, we substitute 1 all over 4 pi epsilon naught to k. So we can write here, can simply write here as phi is equal to k, which is 1 times 4 pi epsilon naught. Multiply it with Q 4 pi. Now, let's simplify everything. So if we multiply these two, we cross multiply this one, this will give us 4 pi divided by 4 pi, that will give us 1. So we have, if we multiply 1 with Q, we have Q, and then what is left with our equation is Q all over, sorry, what is left with our equation is Q all over epsilon naught. Okay, so we have Q all over epsilon naught, which is this one. Okay, which is this one. So there are two equations. There are two equations that we can use to identify the electric flux of an object, or an electric flux. We have this one. Q phi is equal to EA, and phi is equal to Q all over epsilon naught. Now, when do we use equation 1 and when do we use equation 2? So let's dub this as equation 1 and this one as equation 2. So when do we use these two equations? We use equation number 1 if it gives us the surface area of a particular system. But equation number 2 is always used when we are encountering a three-dimensional object or a closed surface. So equation 1 is used primarily in open surfaces, while equation number 2 is used in closed surfaces. Now, having said that one, let's put the equation. So let's before we put the equation into the test or into test, let's first identify what the given variables or describe the given variables in our equation. Okay. So phi is our electric flux, which has the unit of please give this is not Newton. This should be Newton meters per coulomb. Okay, Newton meter per coulomb. Then the electric field is E. Then we have the area, which is perpendicular. We have meter square, charge coulomb, and of course the permittivity of free space, which is 8.85 times 10 to the negative 12 coulomb. Excuse me, coulomb square per Newton meter. So this is coulomb square, okay? Coulomb square. Now let's before we put the equation into the test, we need to understand also one governing principle in electric flux. We call it as Gauss Law, wherein the Gauss Law, the concern of Gauss Law is just the same with electric flux. Gauss Law is applicable when we have a closed surface. Especially, these surfaces are irregular surfaces. Now, Gauss Law is a mathematical relationship wherein the area integral or the surface integral of the electric field over any closed surface, okay? Any closed surface is equal to the net charge of an enclosed system or an enclosed surface with respect to the permittivity of free space. So primarily, the Gauss law is being used when there is a an electric charge present inside a closed surface. Okay, the electric charge is inside the closed surface. So we use Gauss law to to find the electric flux of the system. And how do we use that one is that we get the integral, the surface integral of the electric field passing through the derivative of the area. Now, let's put the equation to the test. Now, I have here a problem. Now, if we are to consider a uniform electric field E, which is oriented in the positive x direction in an empty space, there is a cube lying. A cube of edge length L is placed in the field and is oriented as shown in the figure later on. Now, our job or your job is to find the net electric flux to the surface of the cube. So this is the cube. The arrows here, the purple arrows, I don't know if it's purple, I think it's pink. The pink arrows is your electric field. If the electric field is passing in this direction, what is the electric flux or the net electric flux experienced by the cube? Now remember that the cube is a perfect square. It's a combination, it's a three-dimensional object where the sides are perfect square. So what is the area of a square? Okay, the area of the square is the product of two lengths, L square. That's why in our problem we have here edge length L. Since it's a square, the area of a square is L square. Now the black arrows are what? The normal lines or the surface area, which is perpendicular. Now remember, there are 6 sides in a cube, so there are 6 perpendicular surface area. And not all surface area emits electric flux. So we have the x direction, the x dimension, the y dimension, and the z dimension. So what is the net electric flux experienced by the cube? Let's try to begin first with surface number 1. Okay, there are no values present. Okay, let's just derive the equation by by looking into the cube. Assuming any number could represent letter E or our electric field, but the A is L squared. Okay, cosine theta. So what is the angle at cosine theta? Since this is the electric field is passing in the positive x direction, and area 1, the surface area 1 is pointing opposite to the electric field. So that means cosine 180. If you still remember our lessons in vectors, 180. So we have here EA cosine 180 degrees. Now that would result as negative EA. Why negative? Because cosine 180 is negative 1. Negative 1 times EA, that will give us negative EA. Now let's take number 2. Surface number 2. So surface number 2 is pointing on the same direction with the flux. So it is on the same direction of the flux. So the angle is 0. It's in the positive direction, yes? So EA cosine 0. Cosine 0 is 1. Multiply it by EA, we have positive EA. Now, let's take a closer look on surface number 3. Surface number 3, if surface number 1 and 2 are located in the x dimension, surface 3 and 4 are in the z direction. 5 and 6 are on the y dimension. Now, surface 3 and 4, if we just consider this as a 2-dimension, we can use basic vectors. If we disregard this one as a 3-dimensional object, consider this only as a 2-dimensional object, we can still find the flux. Now, for normally, there would be no flux present here because, of course, the electric flux doesn't pass through this to these particular surfaces. But for the sake of for argument's sake, let's try to find the flux of surface 3 and 4. What is the angle at this particular side? If we convert this into an xy dimension, this would be positive x and negative x. So let's take negative surface number 3 as the negative direction and surface number 4 as the positive direction. So if we try to take a closer look, cosine 80, 180 is negative 1. So surface number 3 is EA, while number 4 is positive, it's positive EA. Okay? How about surface 5 and 6? So 5 and 6 is what? 5 is pointing upwards. So what is the angle that points upwards? It's 90, right? So EA cosine 90 is equal to 0. 0 times EA, that will give us 0. Now, for surface number 6, it's pointing downwards, right? It's pointing downwards. So, this is negative 90, or if we want to use a 360-degree rule, we can write this as 270. Anyway, it's just the same. So, 270, cosine 270, that will also give us 0. So, EA times 0 is equal to 0. Now, we have now the different values for the flux of every surface. Now, this time, let's find the total electric flux of the system. So let's add all together all of the flux. So flux 1, flux 2, flux 3, flux 4, flux 5. So we have negative EA plus negative EA plus EA plus 0 plus 0. That will give us negative EA plus EA is equal to 0. Plus negative EA plus EA is also equal to 0 plus 0 plus 0. That will give us a total of 0. So the net electric flux present in the cube is equal to 0. Okay? The net, okay, the total electric flux passing through the cube is equal to 0. There is an alternative solution for this one. We only take surface number 1, 2, 5, and 6. Why? If we consider this purely as a three-dimensional object, we can automatically say that there is no electric flux present in this one, in 3 and 4. Okay? There is no flux present here. Actually, the same is true with 5 and 6. We can just simply ignore 5 and 6 by taking a closer look with our illustration here. Because the electric field doesn't pass through the surfaces. 3, 4, 5, 6, no electric field passing to the surface. If there are no electric field passing to the surface, then we expect no flux output. Right? There are no flux output. So if we consider only surface 1 and 2, then we can have surface 1 and 2 as our alternate solution and finding out the net electric flux of this problem. We can do that also. But for the presentation's sake, for argument's sake, we can use this one to identify really what is the total electric flux that is being emitted or that is being experienced by each of the sides of the cube. Are there any questions? Please write your answer. If there are no more questions, then thank you very much for joining me in this session. Now, to sum up our session, I would like to leave this question to you. In the concept of electrostatic force, it uses the law of attraction and repulsion. In your own experience as a physics student or as a student, how do you deal with incidents that are positive and negative in nature? Are you attracted or repulsive to these incidents? By what amount of force do you exert so that you can repel these incidents?